Find the refraction coefficient at the breaking depth KBR. In this problem, we are provided with the breaking depth dB, as well as the period of the wave t and the deep water approach angle alpha naught. Alpha naught is the angle formed between the crest line of the wave and the underwater contours of the soil for deep water conditions. As the wave encounters these contours, the wave will begin to turn in the direction of the beach until the wave breaks at the breaking depth of dB. The sketch shown here is in plan view and overly simplified. The refraction coefficient, Kr, equals the square root of the cosine of the deep water approach angle, alpha naught, divided by the cosine of a generic approach angle, alpha. Since we are asked to find the refraction index for the wave when it breaks, we'll add a subscript b to the refraction index and to the generic approach angle, alpha. Now, to solve for KBR, we need to determine the values of variables alpha naught and alpha b. The problem provides us with the deep water approach angle alpha naught, which is 60 degrees. To determine alpha b, we'll write out the coastal engineering version of the law of sines and solve for alpha b, which turns out to be a function of alpha naught, the deep water wavelength, and the wavelength at the breaking depth. As before, we know alpha naught equals 60 degrees, so we're left to find LB and L naught. L naught is the deep water wavelength and is a function of the period of the wave, t. After plugging in 14 seconds for t, we compute L naught equals 1003.211 feet. The wavelength at the breaking depth, LB, equals the breaking depth divided by d over L at the breaking depth. From the problem statement, we know the breaking depth equals 15 feet. The term dB over LB can be determined by knowing the value of dB over L naught, which equals 0.01495. Next, we'll enter the tables between 0.014 and 0.015 and interpolate on a line between the corresponding values of d over L, which is the same as dB over LB since we're dealing with the breaking condition, and it equals 0.04955. This makes the wavelength at breaking condition equal to 302.725 feet. Now we can solve for the approach angle at breaking, alpha b, and after plugging in the appropriate variables, alpha b equals 15.149 degrees. At this point, we can return to our original equation for the refraction coefficient at the breaking depth. After plugging in the approach angles associated with deep water wave and the breaking wave condition, KRB equals 0.7197. When reviewing the possible solutions, the correct answer is C.